The silkworm derives nutritional requirement from mulberry leaves for their growth and development. Variations on the components of mulberry leaves may have some influence in the growth and development of silkworm. The nutritional parameters of mulberry leaves and silk production are directly proportional to each other. The nutritional composition of mulberry leaves vary depending on the soil and other environmental factors of the locality. Moreover, the genotypic characteristics. An effort has been made to determine, identify and analyze the nutritional composition of different varieties of mulberry leaves. The current session deals with quantification of protein, carbohydrate, total carotenoids, chlorophyll A, chlorophyll B, total chlorophyll contents of different varieties of mulberry that are grown worldwide. Nutritional requirements. 16 nutrient elements are recognized as being essential to all plants for their normal growth and development. They are carbon, nitrogen, calcium, iron, hydrogen, phosphorus, magnesium, manganese, oxygen, potassium, sulfur, boron, molybdenum, copper, zinc and cobalt. The two routes of entry of these elements are the roots and the leaves. If the amount of available nutrient in the soil is below the requirement for mulberry, the plant shows deficiency disease symptoms. The usual remedy is to apply the appropriate fertilizer. For quick recovery, foliar spray application is also done. Mulberry is a fast growing plant and depletes soil nutrients at a very fast rate. Therefore, regular input of manures is necessary for optimum production of leaves. Manuring takes a maximum share of the total annual recurring expenditure. Manuring improves both the quality and quantity of leaf yield. Manures may be supplied in an organic or synthetic chemical form or as biofertilizers. The concept of integrated nutrient management (INM) is to increase the efficiency of absorption and utilization of added fertilizers, collection, conservation and utilization of organic waste materials and to employ the biofertilizers. Organic manures. Organic content is necessary to build up the microflora which is involved in nitrogen fixation and the recycling pathways of other minerals. Organic matter can supply the essential micronutrients and also improve the physical, chemical and biological properties of the soil. Bulky organic manure and concentrated organic manure. Examples of bulky organic manure are farmyard manure, compost and green manure. Concentrated organic manure are oil cakes and fish meal. Various types of organic manures are compost, farmyard manure, sericulture waste, poultry manure, biogas slurry and press mud. Compost. It is made by the decomposition of grass or straw or other domestic and agricultural wastes in pits under anaerobic conditions. Lime milk is added to quicken the decomposition. Farmyard manure. This consists of dung, urine and straw that has been used as a bedding for cattle. Fresh farmyard manure is harmful to mulberry roots. Decomposed or partially decomposed farmyard manure can be used. Sericulture waste. The waste used as fertilizers after decomposition include silkworm litter, dead worms, exuvia, pruned leaves, unused leaves, pupal waste, and dead and unused moths. Poultry manure, litter, unfed feed, and dropped feathers which are rich in phosphates are used after decomposition. Oil cakes of soybean, neem, and groundnut are used. Green manures. Leguminous plants which have nitrogen fixing root nodule bacteria are grown as intercrops in mulberry fields, and after their yield they are harvested and mulched and used as green manures. Examples are Senum, Crotalaria gensea, Daincha, Sesbania aculeata, Bersum, Trifolium alexandrinum, and Cowpea, Vigna sinensis, press mud. It is an important byproduct of the sugar factory. Application of 7.5 tons of press mud per hectare is equivalent to 150 kg of P2O5. Advantages of organic manure. It increases the water holding capacity of the soil, improves the physical condition of the soil, and increases the chemical and biological activities of the soil. Chemical fertilizers. The nutrient requirement of mulberry per hectare per year is the highest compared to any other field crops. Mulberry requires 300 kg of nitrogen, 120 kg of phosphorus, and 120 kg of potassium per hectare per year. Nearly 30 to 40% of total cost of production of cocoons goes to fertilizers and manures alone. Irrigated and semi-irrigated conditions, the fertilizer schedule for the variety V1 is 375, 140 and 140 kg NPK per hectare per year. Fertilizers may be applied as per soil test recommendation wherever possible. The first dose of fertilizers is applied 3 months after planting. Subsequent fertilizer application is followed after each leaf harvest and pruning. Straight fertilizers are applied to minimize the cost. Rainfed conditions. The first and second doses are applied coinciding with southwest and northeast monsoons respectively. Regarding nitrogen, when the soil is deficient in nitrogen content, the growth of the plant is stunted. Leaves are shed quickly as they dry up. The nutritive value of the leaves for silkworm feeding is reduced as the protein and water content of leaves become reduced. Mulberry absorbs nitrogen either as the ammonium ion or the nitrate ion. The nitrogenous fertilizers are urea, ammonium sulfate, diammonium phosphate, and ammonium chloride. Phosphorus deficiency can be recognized from stunted growth and very small dark green leaves. Older leaves appear reddish purple. The phosphatic fertilizers are diammonium phosphate and superphosphate. Advantages of biofertilizers. They have no harmful effects. Biofertilizers often produce more than one effect. For example, nitrogen fixers also make phosphates available and in addition release growth promoting substances. Limitations. It is not feasible to meet higher levels of nutrient requirements. Also, inoculum is susceptible to unknown biotic and abiotic factors. Precautions are: chemical fertilizers should not be mixed with biofertilizers. Biofertilizers should be used before their expiry date. Biofertilizers like azospirillum and acetobacter can substitute the nitrogen requirement of mulberry to the tune of about 25%. The intercropping method of mulberry. Mulberry, being a perennial and deep-rooted crop, is planted with wider spacing. This provides scope for intercropping to be accommodated in the interspaces to fetch additional income. The short duration crops are planted in the interspaces of mulberry crops to meet out the above soil requirements. The leguminous intercrops fix atmospheric nitrogen in the soil through root nodules. The intercrops suppresses the weed growth and serve as soil mulches to reduce the evaporation loss of moisture and soil erosion in mulberry plantation. The other crops which can be grown are peanut, tomatoes, soya bean, ragi, gingerly, coriander, black gram and green gram. Compatible crops should be grown. It should not deplete nutrients or compete with mulberry. It should not invite pests and diseases. The water management. The water requirement of mulberry is around 1100 mm to 1200 mm per hectare to cultivate 1 hectare of mulberry. To provide 1 kg of mulberry, nearly 320 liters of water is required. Hence, irrigation water should be used in a more scientific manner as it is going to be a costly commodity in the years to come. To have economy in water application, the field should be prepared with ridges and furrows, and it can also be used as drain channel during heavy rainfall season. Alternate furrow irrigation can also be followed at times of water storage. Drip irrigation, though costs more initially, will save water up to 40%. The saved water can be used for irrigating more areas. Paired row system of planting will also help in saving water requirement both under surface irrigation and drip irrigation system. Frequency of irrigation, it varies depending on the growth stage of the plant, soil type and other agroclimatic conditions. It is once in 8 to 10 days for sandy soils, once in 15 days for clayey soil. Young plants need more frequent irrigation than old ones. Types of weeds and their management. Zimdal reported that weed prevention, control, eradication and management are different concepts and each uses or combines technologies differently. The common weed flora in the mulberry gardens are monocotyledonous weeds and dicotyledonous weeds. Monocotyledonous weeds, Cyprus rotundus, Cori, other name is nutgrass. Cynodon dactylon, aruhambul, also called Bermuda grass. Dicotyledonous weeds, Abutilon indicum, tuthi, also called velvet leaf. Amaranthus viridis, kuppakirai, also called pigweed. Acalifa indica, Paimeni, other name is copper leaf. Weirhavia diffusa, Ukkaratai, also called hogweed. Croton sparciflorus, Yagai Pundu, also called croton. Parthenium hysterophorus, Vidachedi, also called carrot grass. Trianthema portulacastrum, Saranai, the other name is carpet grass. Tridax procumbens, Manjappu, also called Tridax. Integrated weed management. Weed management should aim at maximization of profit by reducing the risk of damage to crops and environment. A large number of herbicides have been evaluated and recommended for a large number of crops in India. They have replaced or in some cases supplemented traditional practice of hand weeding towards weed control and economization of overall production cost. The chemical method, though proved more promising, has led to many problems such as weed flora shift, insurgence of herbicide resistant weeds, gradual population buildup of perennial weeds and inhibition in growth of non-target microflora, besides residue problem in the environment and marked reduction in tillage practice. Even the spectrum of weeds killed by herbicides in most cases is narrow. Herbicides therefore cannot be a sole and foolproof strategy. Thus, no single method, example manual and mechanical, biological or chemical, could reach to the desired level of weed control efficiency in certain location or across locations, mainly because of the vast diversity of weeds in crop fields. There also occurs a continuous dynamics both in population and biomass accumulation of weeds in crop field ecosystem on temporal scale, mainly due to changes brought about by man in crop cultivation and management practices. It has been witnessed that today's weed of minor importance assumed importance gradually and became a major weed of regional or national concern in course of time. Cultural, mechanical and chemical methods of weed management. Cultural, the stubbles and the roots of weeds are removed while preparing the land. Well decomposed manure is used to avoid dissemination of weeds. The implements are cleaned before use. The channels are kept free of weeds. Fryer stated that a good crop is the best weed killer. Cultural or ecological methods exploit crops' competitiveness, growing environment, and management practices towards producing a good or healthy crop. Mechanical control methods. Country plow or power tiller rotavator is operated after pruning in the interface. The weeds are removed by hand hoe. Chemical method. For annual weeds as post-emergence application, the contact herbicide paraquat is used at 2 to 3 liters per hectare. For perennial weeds, the systemic herbicide glyphosate is sprayed at 10 ml with 10 gram of ammonium sulfate per liter of water as post-emergence application. Usefulness of chemical methods. Herbicide is the most potent single tool towards weed management if used judiciously on the prescribed guidelines. It on global basis has the highest consumption, production and market share among all pesticides. Herbicides, particularly pre-emergence ones, control weeds right from the beginning of their germination and thus prove to be more efficient than many other methods of weed control. Herbicides can control weeds having morphology similar to the crop plants. Example, Phalaris minor, Avena fetua, Lolium temulentum, etc. in winter cereals like wheat, barley and cultivated oat are easily and efficiently controlled than any other methods. Even trained manual laborers cannot identify these weeds growing in intra-row position at the early seedling stage and leave them unweeded. This is revealed when they come to flower by means of the difference in their inflorescence. Most herbicides prove to be more economical than mechanical and manual methods, particularly where manual labor costs higher. Advantages. IWM is considered a more practical approach, more effective in the long run since combination of methods will take care of weeds in totality and prevents seed production of weeds and enrichment of soil seed bank. It provides longer and continuous control of weeds than any individual method since it normally overcomes the existing lacunae of individual method of weed control applied in isolation. It may reduce or eliminate the chance of occurrence of weed flora shift, herbicide resistant weeds, preponderance of perennial weeds, etc. in an agro-ecosystem. Its environment or eco-friendly. Ill effects on soil microflora and microfauna and degradation to environment through herbicide residues could be reduced by adapting IWM, which advocates usage of herbicides at the lowest possible rates. It may to some extent be complementary to integrated pest management through continuous control of weeds which otherwise allow or cause many insect pests and diseases to harbor upon them. Limitations or disadvantages. An IWM approach may not be uniformly applicable to all crops across locations. It is highly site specific and crop or cropping system specific based on number of factors comprising of soil, crops, climate and production or management practices adapted. Integrating methods of weed control are mutually compatible, supportive to each other and matching the diversity of weed species is not an easy task, but requires a lot of researches to be carried out on form for suitability or compatibility and economics and then proper refinement of the results for implementation and social acceptance. Otherwise, it cannot be a successful IWM strategy. A model IWM designed for certain situation may not be operative constantly or repetitive over the years, since the relative importance of the methods under integration may vary at degrees in course of time based on weed species and population distribution and overall weed infestation. Need may arise in between to incorporate a new method or exclude an already existing method for a workable integration of weed control methods under certain situation. In this session, we discussed about the symptoms of nutrient deficiency of mulberry, types of weeds and their management, and herbicide application methods. We also discussed about integrated weed management. To summarize, mulberry is a fast growing plant and depletes soil nutrients at a very fast rate. Therefore, regular input of manures is necessary for optimum production of leaves. Manuring takes a maximum share of the total annual recurring expenditure. Manuring improves both the quality and quantity of leaf yield. Manures may be supplied in an organic or a synthetic chemical form or as biofertilizers. A large number of herbicides, since their discovery has been evaluated and recommended for a large number of crops in India. They have replaced or in some cases supplemented traditional practice of hand weeding towards weed control and economization of overall production cost. The chemical method proved more promising has led to many problems such as weed flora shift, insurgence of herbicide resistant weeds, gradual population buildup, preponderance of perennial weeds and inhibition in the growth of non-target microflora, besides residue problem in the environment and marked reduction in the tillage practice. Even the spectrum of weeds killed by herbicides in most cases is narrow. Herbicide therefore cannot be a sole and foolproof strategy. Thus, no single method, example manual and mechanical, biological or chemical, could reach the desired level of weed control efficiency in certain locations or across locations, mainly because of the vast diversity of weeds in crop fields. There also occurs a continuous dynamics both in population and biomass accumulation of weeds in crop field ecosystem on temporal scale, mainly due to changes brought about by man in crop cultivation and management practices.